A triangle is convex. Well, is this true sometimes, always, or never? Well, this is a pentagon I'm demonstrating with. Just to remind you what convex is, I pile up the snow on the roof and it caves in. And that figure is concave. Of course, we don't care about that. We want to know convex, the antithesis, the opposite. I draw this triangle, this arbitrary triangle, and if I cave the roof in, oops, still a triangle. I can't seem to arrange it any way that I've got my caved in roof. So this triangle is always convex. Our statement reads, a decagon is regular. Sometimes, always, never. Well, there's an example. I can see a decagon here, the shaded figure, and I've got 10 congruent sides, 10 congruent interior angles. All I need is a counterexample, and that's a counterexample. 10-sided figure that is not equilateral, not equiangular. That tells me this is sometimes true. Well, drawing a triangle that's not regular is pretty easy because that's it. The only way it would be regular is if it were equilateral, which happens to also be equiangular. As long as it's not that, it's not regular. Well, here is an arbitrary convex quadrilateral. All I need to do is take one vertex, imagine a lot of snow on the roof, and it caves in. That is a concave quadrilateral. So is it possible to have a pentagon that is equilateral but not equiangular? Well, let's see. I've got 5 congruent segments here. I would just have to bend them around, bend these pieces until I could get those two to, and look at that. There is a equilateral pentagon that is not equiangular, therefore not regular. Well, let's see if it's possible to draw an octagon that is equiangular but not equilateral. I've got here 8 segments, and I've got the same angle between all of them. I just have to join the figure up, I guess. And let's see if we can do that. I bet if we extend this one down over here and maybe move over like this, hey, there you go. That looks like an 8-sided figure which has equal angles but not equal sides. Let's explore line symmetry with these 4 given regular polygons, starting with the triangle. I'm going to take a reflection of the triangle over this given axis right there. It flips onto itself. That is an axis of symmetry. Notice I rotate like this, and when I reach this point, see, I'm lined up with another vertex. That would be a second axis of symmetry. I come over here, I'm at a third axis of symmetry. Of course, I can see an axis here, but I've already counted that one, as well as this one, as well as this one. So I see 1, 2, 3 axes of symmetry. And that would be for the regular triangle, also known as equilateral. So let's check out the regular pentagon. Regular pentagon, I see 1, 2, 3, 4, 5. Of course, I see this one, and I'm now repeating, etc., etc. So again, I see 5 axes of reflection. I guess we see where this is going. 5 sides, or 5 vertices, 5 axes of reflection. Let's try the hexagon. I've got 1, 2, 3, 4, 5, 6. I come over here to number 7 and I'm already repeating. So even though these axes of reflection occur not aligned to vertices, I have an even number of sides, I still have 1, 2, 3, 4, 5, 6. I still have the same as the number of sides. That's going to be 6. And we'll just finish this out with the regular octagon. So I've got one. Well, you know, let's make this octagon a little bit bigger so we can see it. This figure is hard to see. I've got 1. Do I have an axis here? That's 2, 3, 4, 5, 6, 7, and 8. And beyond that, I'm repeating. 8 vertices. I've got 8 axes of reflection. So there you have it. 3, 5, 6, and 8 sides. 3, 5, 6, and 8 axes of reflection.